Hello, and welcome to your second lesson in Module 3 for Alg3Trig. Today we're going to talk about logarithms. And when we talk about logarithms, it's important to understand a little bit of history of logarithms and why they are called logs. One of the things, if you Google a man's name named Napier, what you'll realize is that this particular person back in the 1700s or 1800s was intrigued by the question of, if you have something like 10 to the first power, that is equal to 10. And if you have something like 10 to the second power, that is equal to 100. But there should be a way to raise 10 to some power, to get any number in between. For instance, 10 to the 0 would give you 1, so you could get that real easy. But everything in between these numbers, right? Like 10 to what power is 13, for instance? Or what about 10 to what power is 20? There has to be a number that I could put here to make this happen. And he sat in his tower and thought of this up and recorded it. And it was later published in some logs, literally log books. And that is why this came out to be called a log. So what is it? It is really another way, and this is the way he figured it out. It's another way to write down an exponential. And so he defined the logarithms by their definition in an exponential form. So one of the things that's really important to understand is that this base is the base of the exponential form. So what happens is this b goes right here. And what ends up happening is he created, in order to figure this question out, to figure out the exponent that would make this happen, he actually defined the inverse. And the inverse is to switch the operation. So the answer becomes the exponent, right? And then the inside of the logarithm becomes the answer. So they switch this would be read log base b of a. So the a becomes the answer is equal to x. So the answer becomes the question, and that is the inverse. All right, there are two special kinds of logarithms. One of them is, what does it mean to be log base 10? So since he developed these with log base 10, because 10s are easy, the basis of the decimal system, the first logarithm is actually just log. So if you ever see a log without a base, that's actually log base 10. It's important to remember that. There are a lot of things like this in math. For instance, as we learned in the last lesson, the square root is the first root that was developed. We do not put a 2 there. That would be a bad thing. So if you don't see a 2, it's really the square root. But anything else, 3, the fourth root, they would have a 3 or 4 there. So if you see a log and it doesn't have a base, it's log base 10. And I will tell you that sometimes people will put a parentheses here to make sure you understand log of what. So this would be read log base 10 of x, or just log x. Later, another person, his name is Euler. Now this is a German name, so it looks like to us that this would be Euler, but this sound right here in German is the sound oi. So Euler came up with this very interesting constant in the world called e. He named it e for the exponential function. Some people would say he named it after himself. And e is 2.718, and then there's other irrational numbers after this, a lot like pi. And this was developed in his study of actually interest rates, along with other naturally occurring phenomena. So it is called the natural constant. You'll see it in chemistry and biology and finance class. It's so important that when he tried to go to find the answer, kind of like what happened up here with Napier, he decided to make a special logarithm called the natural log. And the natural log is denoted ln. And you might recognize these two things. Again, some people would have put a parentheses here, some people don't. These two functions are on your calculator. So if you have an old TI, an old Casio, if you look at Desmos, log and ln are there, you will not see these two. All right, so let's take a look. Let's just start off by how do we define an exponential from a logarithm or vice versa. Basically, we're going to this first definition here. And this is actually fairly easy as long as you remember that the base here is the base of the exponential function. So this base becomes the big base. right? And then since we're just doing inverses, watch how this works. We're just doing 7 to the second power equals 49. And you might be saying, what are we doing? We're just understanding that logarithms and exponential functions are part and parcel of the same thing. And understanding how a logarithm works makes it less intimidating. So for instance, this one would be 2 to the 5th is equal to 32, right? 2 to the 5th power is equal to 32. And you may not recognize the logarithm's answer, but you should recognize that these are true statements, right? 2 to the 5th is 32. 7 squared is 49. So if I came over to this one, right, you wouldn't want to say log of 0 or something. This is, as I mentioned, log 10. So this would be 10 to the 3rd is 1,000. And of course, that is a true statement, right? 10 to the 3rd is 1,000. Okay. And then we get into some interesting things from yesterday's classwork homework assignment. So if you have not done the homework assignment on exponentials, number 4 is going to be a little confusing. But if you have done it, same with number 5 and number 6, it will make sense. So 4, let's write down the expression. 4 to the -3 is 1/64th. And you might say, how is that a true expression? Well, let's talk about some key things about exponents. In the world of exponents, negative exponents actually mean fractions. Why? Because negatives go to the denominator. So the way you should read this is 4 goes to the denominator and becomes 1 over 4 cubed. And then 1 over 4 cubed is 1/64th. And that's the why, right? That's why this works. And this is a little bit of a review, again, of last time, because there's a connection, obviously, between logarithms and exponentials because they are defined as the inverse of each other. So let's take a look at this one. Again, very helpful if you have done last night's classwork homework. 2 to the 1/3 is equal to 2. So why is that? Sorry, 8 to the 1/3 is equal to 2. Sorry if I misspoke. So 8 to the 1/3 is equal to 2. And you might say, why? Why is that true? Unlike up here, we're just looking at scientific notation or just basic squaring things, really like multiplication tables. The reason this is true is that 8 to the 1/3 really means the cube root of 8, right? And of course, 8 is 2 times 2 times 2. So the cube root of 8 is, in fact, 2. So that does make sense. But again, you had to have done that other homework. This one, too, 9 to the 3/2 is 27. And so that would look like this. And this one will take a little bit more time to understand why this is a valid statement. But it's not hard. Let me show you again why this is true. Again, a little bit of review here. 9 to the 3/2 really means the square root of 9 raised to the 3rd power. Please remember that fractional exponents, the denominator is the root and the numerator is the exponent. So what is the square root of 9? Well, that's equal to 3, right? So that becomes 3. And then if I cube this, I would get 27. So a logarithm will always come from a true fact in the exponential world. That's an important thing to remember as a student. Okay, so then we come down here to some ln problems. If you have the old notes and this wasn't updated, please fix that typo. I have the correct version of the problem here. Okay, so for instance, if I looked at this, and now I have an equation, what I would do here is I'd make sure I understand that there's a little e here. And so I would get e to the 4th power is equal to x. And that's going to be important later when we learn about equations. So we're just kind of getting you to set up. Don't be afraid of letters, right? So e to the 4th is equal to x. And then over here, this one also is a base of e. So if I were to look at this one, this would be, don't forget, it's very important, this little cycle. E to the 1st power is equal to that. And in fact, I'll show you why that makes perfect sense. So e to the 1st power, which of course would just be e, is equal to 2.718. And that loops us right back to our definition. E is 2.718. So that does make sense to us. All right, that completes the first video. And we'll make a second one with going the other way around and also meaning going from exponents to logarithms and also some other applications of how we would use logarithms in simplifying.